everybody! Welcome to Chem 163, as the screen is about to tell you shortly once I get everything set up here. There we go. Hooray! Oh no, I ruined it. Hold on. I broke everything because I clicked over on the Discord. So that's going to happen again. Sorry. And you had no audio to hear that. Hi, I'm Wes Hillman, and nothing is working. Why isn't it working? There we go. It is not working because there is a cat already here to bug me. My name is Wes Hillman. I have my degree in inorganic chemistry, so you are in good hands, especially your 163, because this is where inorganic chemistry actually comes into play. And yet we don't talk about it. Please address me as any of the following. I prefer just to be called Wes. Like, that's perfectly fine. You can call me Professor. It's not my official title. My title is faculty, but I don't mind being called something above my pay grade. I had a student one quarter call me boss, and I was like, "Ooh, I do like that. You can definitely call me boss." So that's on the list there. And then I play so many stupid role playing games and other nerdy shit that like any derivative of orc that you want is fine. Um, the one thing I just ask that you don't call me, please don't call me Mr. Hillman. It makes me feel old. It says I'm only 38 there. Eventually, I don't know if I'm gonna be able to put only. I don't know. You start to feel it when you get to your mid 30s. Here's my email. The only reason that I'm writing my email out for you to note down or keep in your notes is that you may need to email me directly, and Canvas might be down, or maybe you want to make sure it goes through quickly. Canvas sends out batch emails, so like it sends email every like minute or two. But sometimes it gets caught up. Like on the first day of the quarter, especially in the fall, Canvas can take up to like 30 minutes to do something because it's just so behind on all of its activities and processes. So if you want to get to me directly, immediately, email me through Google and it'll be fine. So there's my email for that. And then finally, office hour. How do we deal with office hour when we don't have an on-campus class? This is a hybrid. We'll talk about what that means in a second. But I'm not physically present on the campus other than for the labs, and so I'm unavailable for physical office hours. All my office hours are going to be conducted virtually via either email or Discord. We have not gotten the class Discord set up yet because nobody has emailed me about it. So we'll talk a little bit about that in just a moment when we talk about the syllabus. Hi, everybody. I see everybody in the chat now. I have a different monitor setup than I had last quarter because I went and bought a bigger monitor, but my monitor is like way over to the right, so chat is very far off to the side, so I'm going to do my best to keep looking in that direction, but hopefully I won't miss any questions. Alright, so the gist of how this works is that I have this little button here, so this is the slideshow. I can click on this, and this will be like my little canvas that I can draw all over, so let me get this out. So we I could just draw all over this. So we're going to solve problems on this like virtual whiteboard I have. It's just Photoshop. And then when we need it, I have a calculator hidden over here. I'm going to hide the chat real quick. So I have this calculator that I'm going to reveal when we need to use a calculator. So you can see what I'm punching into my calculator at all times. This class is particularly math intensive. You're going to be doing a lot of algebra. A lot. Like 162 levels of a lot, and then even then more, I would say. So very, very, very important that you have a functional calculator and have something to write on, obviously. We'll get to more details that you will need in the syllabus, which we're going to do right now. Every student in this course has taken 162 and 161, probably at this college, if not probably at a college that has used Canvas, so you're not Canvas novices. So I anticipate that you can log into Canvas and you know how to do so. What I will do is I will put this over here so that I can see it, and then we'll go like this. And so, boop. Give me a second here. Yeah, that's fine. Okay. So this is our course page. This is just the announcement I just sent out. So if you go home, On the homepage is all just like, here's what all of the tabs do. You aren't going to see all these tabs down here because I've disabled them. And you might not be able to see the quizzes tab because there aren't any quizzes yet. I will mention what that's all about. The one you really want right now is just modules. And in the modules tab are all of the lab things that I uploaded over the weekend. So this is all the experiments that we're going to do. And then all of the chapter content that we are going to be covering in this course. Note that there are no slides for Chapter 20. That's because I have never gotten to Chapter 20 in teaching this specific version of the class. When I was going to do Chapter 20, that was in March of 2020. And you could probably guess what happened in March of 2020. Yeah, that's right. COVID started. So all of my classes got canceled and we just never got to it. So I never made the slides. That was the last time I taught this course. So I'm going to make those slides and they will eventually be available. What we're going to work on right now is the syllabus. I'm going to close this window and get you a different window that is easier for me to manipulate so that I can show you the syllabus. But let's talk about what exactly you've gotten yourselves into. Don't worry, if you picked Valerie's class instead, it's no better. So you're in good hands that Chem 163 is just going to be this bad, regardless of which instructor you have. All right, let me put the schedule on the screen here first. See if I can fit it all on here. No, actually, that's the best I can do. Okay, so here's weeks 1 through 8. You can see that on the right side, I have some things that are in bold blue. Bold blue means, hey, you're going to do this in person. You're going to see me. I'm going to direct you on how to accomplish the task, and you're going to refer to your lab documentation that you brought there. You'll also notice there's a lab 0. I'm going to provide you with lab number 0. So lab number 0 here is not on Canvas. Don't worry about it. I'm going to print that out and give it to you so that each person has a copy for them to fill out because it's a worksheet. It's not something that you're going to do as an assignment like all the other labs you're going to do in the class. So other than that, every week we are going to be meeting for something. That's why these are all in blue. You'll notice that there's nothing on the first week. So this Friday, do not go to campus. If you do, you're going to find this nice sign on the door to Whitehorse 345 that says, no labs week 1. Check Canvas and the syllabus for updates. And you'll be like, well, shit, why did I drive all this way on a Friday morning? Unless you have another class on campus, then sure, by all means, go and stop by and say hi to the lab tech, I guess. He's friendly. On the syllabus is just a generic schedule of what we are going to be doing each day. I anticipate it's going to be roughly 2 weeks per chapter, and there are 6 chapters, 13, 14, 15, 16, 17, and 20. Exam dates are listed in blue, which means that we are going to be taking them during the lab period. So during week 5, there is no lab. Instead, you're going to come to campus and you're going to take an exam. Exams in this class, 163, are in person, okay? If you've had a class with me in the past, this is very different. In the past, everything was online. You could do all your quizzes and stuff on Canvas. Not anymore. Now I want to assess your actual work in a timed setting without any resources at all. So that is going to be very different from in the past when I said, yeah, use whatever the fuck resources you want to. It's online, right? Not anymore. Now I have to test that you actually know this shit. So make sure that you understand how to do all of the problems for the 2 exams. So exam number 1 is week 5. Exam number 2 is week 10. And then, of course, the final, which is special. We'll talk about that in a little bit. Now, to facilitate that, I'm going to change the course as well from how I've done 161 and 140 in the past. So let's just keep going here. On this page is just a table of how many points each thing is worth. You'll notice that the quizzes are split into chapters, so there will be 1 quiz per chapter. The last quiz will just be an extra credit quiz. We'll talk about that later. Then we have our exams, and then we have labs, and then the final. I have a point breakdown for you. Canvas, I believe, will attempt to give you a percentage for your grade. If you don't trust it, which there are reasons not to trust it because Canvas doesn't understand how to do grades super well. You can compute your own percentage by tallying all the points that you have divided by all the points you could possibly get, and comparing it to this scale as a percentage. So, how many points do you need to pass the class? You need 75% of the points. Again, that is different from 140 and 161. That is much higher. In 140, I ask you to get a 72. In this class, I ask you to get a 75. All right. Finally, here are a bunch of links that I want you to look into should you need to use them. So first and foremost, the student rights and responsibilities link is posted right here. It basically just leads you to a policy about plagiarism and cheating and academic honesty. Review that. It's important that you don't cheat in this class. I will and have forwarded all instances of what I believe were plagiarism to the dean. Students have been kicked out of my course for plagiarizing in the past, so be careful. Tutoring is probably the next most common resource that people ask about. We have a tutoring center on campus in Rainier. It says right there, 119. I didn't remember the number. We specifically do have a chemistry tutor. Her name is Candace, and she does a fantastic job, and I believe that the on-campus tutoring center is open now. There is still online virtual tutoring if you want to sign up for their Canvas page and then do tutoring through Zoom. Super helpful resource. Candace can do anything that I can do in this class, and then some, because she does all of the classes. So if you have any questions, ask either me or Candace, and you're in good hands. The Writing Center, not going to be super relevant for this course because we don't do a ton of written work. But I leave it there just in case you need it. Like, if you're in English 102, you're going to definitely want to talk to the Writing Center. And then finally, the IT Help Desk. If you have issues logging into your email or your Canvas password doesn't work or something is weird, only 2 people can help you, and neither of them are me. So the first one is eLearning. eLearning does everything with Canvas. So if you can't log into Canvas, contact eLearning first. But if you can't log into like your student email or other stuff like that, then you email the IT Help Desk, and that's where they go. They will help serve you in whatever capacity you need. So remember, I cannot diagnose technical issues. If you can't log into Canvas and there's like an exam tomorrow and you can't get any of the slides, I can't help you. So make sure that if those sorts of issues arise, that you are on top of them. I had a student one quarter who basically told me like week 5 that he hadn't been able to log into Canvas. So half the quarter had been gone. They had missed all of their assignments. And like, yeah, that's no good. Obviously that I can't help you there. So they ended up having to drop the class. So make sure you don't fall into those sort of pitfalls. The rest of this really you can just read. So I'm going to just quickly go over the important stuff. The textbook for this class is online. Everything is in Canvas. I have split up all the chapters to have specific links. If you were in my 140, this is not the shitty OER textbook that somebody pieced together and I copied and then had no time to fix. This is an actual really good textbook that has tons of practice problems, illustrations, and things like that. And we're going to refer to it all the time, basically. Let's see here. You can find that at this link in the syllabus. I also have it linked in Canvas. You are going to need some sort of calculator. Let me put the calculator in the front here. We'll just do this for now. Your calculator needs to have very specific functions on it. And those functions are log, 10 to the x, and natural log. So we don't use sine or cosine. You also should use square root. We're going to be doing a lot of square roots in this class. Cubed root or xth root you can definitely do as well. We will be using calculators in person, which I do not necessarily have enough of. It depends on how many people forget their calculators. So you will need to have some sort of calculator, both for physical presence in the classroom and to work online. So if you have your calculator in front of you, that's great. Excuse me. If you do not have a calculator handy, you can either use the Windows calculator along with me as we need it, or you can use the one at Wolfram Alpha. Wolfram Alpha is a text line calculator. You just type stuff in, and everything will be fine. Finally, you need a periodic table handy. You can use p-table. We're going to be referring to the periodic table all the time for things like molar mass. We'll talk about Lentech when we get there. You might remember Lentech from 140 and 161. There's our schedule. So this class is Monday, Wednesday. We're going to meet on Monday, which is today, Wednesday, which is 2 days from now. 2-hour lectures, 4 hours total per week, and then we'll meet on Fridays from 9 to 11:50 in the lab. Don't be late. Friday labs start at 9 a.m., which is going to suck for me a lot, actually. Because not only do I have to get up even earlier, I have to drive. So I will try my best to be on time, but make sure that you aren't an hour late because you won't have enough time to do the experiment. Let's talk about attendance. Anything that is online, attendance is optional. If you are watching the lecture right now, fantastic. Please ask me any questions you might have, because that's kind of my purpose here, is to aid and assist you in whatever means that I can. If you cannot make the lectures, you can watch them whenever you want to, because they're going to be archived on YouTube forever. I still have every lecture that I have ever done online since the start of the pandemic, which I guess would have technically been spring 2020. It's all there. You could go watch it. There is no 163 lectures, though, because I was doing in person before the pandemic started. But all my other lectures are on there. It's just YouTube keeps them forever. So that is handy for you if you have like class during, or not a class, but like work during this time or something. The one thing that you cannot miss, you must be present physically on campus, is the Friday stuff. So that's going to be any lab, and then the exams are the final. You cannot make these up. Absolute hard no. You cannot make any of these things up. Because, one, the labs are only offered once a week. My schedule is unique to Valerie's, so our labs are not going to be the same. If you miss a lab and you can't make it, you need to let me know immediately so I can try and get you into Valerie's lab. And even then, if she's not doing that lab, you're kind of SOL. And I can't give you credit for it. If you miss an exam, just no. Do not miss an exam. If you do that, we will cross that bridge when we get there, and I guarantee you won't like the outcome. It will be somewhat fair. And by somewhat fair, what I mean is I will take your second exam and I will duplicate your score. And both exams are really hard, and you probably don't want to do that. So yeah, I have to be a stickler on attendance for the Friday stuff because hybrid, in person, and these are all things you just can't make up. So, like, normally I'd be like, whatever, like, you have a life, obviously. But I am going to operate this class on the assumption that you signed up for my course, 163 HY, with the intent that you saw on the lecture schedule, oh, I have to be in person on Fridays, and you have committed to that by remaining enrolled and paying tuition. So please abide by that so that we have as few difficulties as possible trying to schedule stuff. You can read all this on your own. Let's talk about quizzes. In the past, I would do quizzes on Canvas for 140 and 161. 163 has a lot more math. And I feel like Canvas's system of not awarding any partial credit is kind of awful for 163, because you're going to do these really long problems, and anywhere along the way you could make a math error in your algebra and get the wrong answer, and Canvas would just be like, sorry, wrong. I don't like that. So what we're going to be doing instead is you are going to be given hard copies of the quizzes in the laboratory. Not the first quiz, because I obviously don't have something to give you this week. And I'm also going to just upload them to Canvas, and so you'll just have the paper copy of the quiz that you can print out or do whatever. What you're going to do is I'm going to give you the quiz well in advance. You're going to have like a week or two. So like I have to write the first quiz. I'll probably put it up there like either tonight or tomorrow. And it'll be available. You're going to have a week or two, and then I'm going to set a deadline. We'll talk about how deadlines work in a second. But at the deadline, your quiz will be due. Your options are turn it into me with a physical paper copy, i.e. on lab day, you can just hand me your quiz. Or you can upload a copy to Canvas using Google Sheets, just like you would do for a lab in the past. If you choose the virtual option to upload something online, then you're going to need to photograph your work and then import it as a series of images into the Google Sheet for each question. I'm going to have these like big blank areas that are going to say, import your work for problem 1 into this space. And then you could just take your picture and put it in there. And then you can upload it to Canvas before the deadline closes. If that is too much work, you can always take the paper copy, print it out, and then hand it to me on lab day. Either medium is fine. I will accept both of them. If you are using the virtual option, I do have some requirements that I will impose upon you. So if you provide an image of your work, what you are going to have to do is somewhere in your work, you're going to have to indicate your answer. And once you have done so, you need to initial beneath your answer. If you do not do that, I will not give you credit. Okay? Your initials need to be clearly written on your page after each answer. If you are doing the paper copy, you do not have to do this, because this is basically a copy-paste, sort of like lowest effort proof that I can do. You are going to watermark your own images with your signature or your initials so that somebody can't just copy your work and then paste it into their document. Okay? So it's got to have your initials. Can you Photoshop that? Yes. Will I notice it? Almost certainly. So just be careful if you're going to think about cheating. I will probably find out. For quizzes, do we turn them in whenever we want to, as long as they're turned in by the due date? If you are turning them in online, then yes. If you are turning them in physically to me, then the only day to do that is the lab day. So if you leave your quiz at home, you're going to have to print out another copy during the 3-hour lab period, and then quickly fill it out, which will suck. And then if you are copying, I will notice in the lab that you are copying your quiz, because I walk around the lab, and you should be working on the lab and not writing stuff down on a quiz. So make sure you do it all in time, and if you are turning it in with the physical version, make sure that you bring it to campus. Exams are in person. Exams are going to be like the quiz problems, except that you just have no resources. All of your stuff is going to be done in the lab period. You have as long as the lab period is, so I'll give you 3 hours to do the exam. But the exams are designed to be 90 minutes long. So if you need more time, that's totally fine. I'm on campus until 11:50 anyway. Excuse me. But the intent is that you will be in there, and you cannot use any resources at all. You get a calculator, periodic table, and the exam, and that is it. Can I download it and do it on tablet and hand it online? Yes, absolutely. So any format that you can interact with virtually is absolutely fine. All I ask is that if you are turning in a quiz online, that it is a Google Sheet. So you may have to copy and paste your work from your tablet PDF that you were writing into the Google Sheet, because I only accept XLSX files. That is just so that you don't send me incompatible formats that I can't open. Canvas will just automatically reject them. If you aren't sure, send me an email of what you are trying to do, and I will guide you through it further. The final. Let's talk about the final. The final is weird. The final is standardized and is comprehensive over the entirety of Chem 161, 162, 163. This is not a typo. You are being tested on an entire year's worth of chemistry. There is a lot of content there. You will have done 30 weeks of this stuff. Fortunately, chemistry builds upon itself constantly. So it's not like you can get to the end of the quarter and then forget how to do density or molarity or things like that, because we're going to be just using those constantly. It's the things that you're going to forget are like, not Lewis structures, we do that a lot, but things like quantum mechanics. What's an sp3 orbital? What is the Pauli exclusion principle? Thermodynamics. What is enthalpy versus internal energy? How do I calculate the heat capacity of something? Like stuff like that we don't do as much. But you need to know those things. So it is very important that while we are going through the quarter that you are reviewing stuff from previous quarters. That said, traditionally people do really well on this. Like, surprisingly well. I always thought that, like, people are going to forget all their Chem 161 stuff. And no, it turns out people do remarkably good. At least in my past experience, this will be the first time I'm going to be taking data for this exam for students who've taken this course online. So we'll see how that works out. But I do curve the exam. I do provide you with some worksheets. I haven't gotten those up online yet, but I have a bunch that will have practice problems for the current chapter you're working on, and then also previous chapters. I don't know if they have answer keys. I have to look into that. So I still have some construction left to do for that. Here's the lab schedule. Again, lab 0 I will present to you in person. The rest you can actually print out the documentation. We'll talk more about that like next week. I'll bring up lab number 1 so that you can see it and give you a little rundown about how to turn in labs and stuff like that. The one thing that I do want to point out that is different from 161 and 140 if you've taken it in the past, labs are going to be split into 2 pieces because this is a hybrid course. The first piece is going to be everything pre-lab. So if I go over to, let's see here, hold on. I gotta add a window. So, window capture. And yeah, that's the one I want. So we'll just go boop. Okay, you don't need all of the tabs at the top there. All right, so if you scroll down to all of the labs, you're going to see a bunch of links here. So this is the documentation, the PDF file that you're going to want to refer to. You're going to see a pre-lab assignment and a lab assignment. And if you go into the assignments tab, you probably can't see any of these yet because I haven't published them. But here on my side, you can see that I have a pre-lab and a regular experiment set up for each one. The pre-lab is going to have a due date of the start time for the lab, which is 9 a.m. sharp on Friday. If you don't turn it in by that time, you can't make it up. You do not get those points, okay? Because it is intended to be a pre-lab. You do this before going to the lab. Then you're going to have the lab assignment, which is going to be the remainder of this. So there are 2 chunks that you are going to have to manage in this class. And those 2 chunks can be found here in the lab assignments. So more on this later this week when we start talking about labs. All right. I do have an NQA policy. If you miss any one assignment for any reason, excepting the exams or the finals, so this does not apply to exams or the final, it also cannot apply to lab sessions that you've missed, just the lab reports and their due dates. I will extend the deadline, no questions asked. So I realize that shit happens to everybody. I mean, it's going to happen to me at some point inevitably. And I'm going to have like, oh, I have to cancel lecture, or, oh, I'm going to arrive 20 minutes late, or something like that, because I don't know. Things happen. And so I can accommodate you one time. I think that that is fair. If you have taken on too much and you just need like a breather and you just can't get to that lab report today, but you'll have time tomorrow or the next day, yeah, use the NQA. That's what it's for. I do require that the first instance, regardless of the circumstance, excused or not, uses your NQA. So regardless of, oh, I can't do it, I'm too tired, or my parents died and I have to go to their funeral, I will require you to use the NQA on the first occasion. Obviously, the second one, I would be like, holy shit, dude. Like, but I still have to make you use the NQA if you haven't used it yet. Okay, so some circumstances I can work with, but the first instance is always NQA. Okay, just because there's usually not a second instance, and if there is, we have other issues that we need to discuss. You can read about your grades, partial credit, etc. If you have CDS accommodations, make sure that you get those filled in by CDS. Usually they will email me a notice that says, hey, this student has CDS accommodations. And then I can talk to you about if you need anything like specific. So like if you have like, you need like the PowerPoint files in a different format, or you need different time accommodations for quizzes, or you need to take them at the testing center. We could totally do all that. Just send me that documentation from CDS, and then if you have other stuff you want me to know about, please email me. Academics honesty, you can read that on your own. Don't cheat. I will find out. Trust me, I will find out. I've done this for too long. And then all the stuff that this course is about, you can read that too. All right, that's the fast version of the syllabus spiel. There's my email. This slide is unfortunately obsolete because I don't have office hour here. So let me get the pen out. So let's see here. Because I didn't read this. So this is unfortunately not valid. So office hour is on the class Discord once somebody sets it up. If anybody is interested in being in charge of the class Discord channel and you want to make a channel, you can send me an invitation code. Well, first ask me for permission. I will honor the first request that I get. Do this by email. Don't post the invitation link in the chat because you can't, for one. And two, this is a public video, so anybody can see it. And we only want students in the class Discord. So first, let me know if you want to make that channel. I will email you back saying, sure, please do. And then make an invitation link for the class. Make sure that the invitation link is set to never expire and infinite uses. All right. Last bit of information and advice that I have before we actually start doing course content is stuff that's on the screen. As a department, we in the chemistry field at Everett Community College have asked students many, many, many questions. And at the end of the quarter, we try to collect data so that we can analyze what students found to aid them with their success and what students found difficult. We also ask them things like, how many hours per week did you work on this content? Or how many times did you meet with other people? Or did you find it easy? Did you get the grade you expected? That sort of thing. And so here is what we have summarized. And this obviously sounds really generic, but it's because it's the average student. So keep that in mind. So very, very, very important. Anything you can do before lecture helps you. If you read the text and take any notes at all, that's going to help you come in here with a basic understanding of what's going on. And even if you just come away knowing like what terms are, so like, oh, I remember reading the word equilibrium. I don't really know what it is, but I read that word. That's better than coming in completely blind and having no idea of anything. So do your best attempt to try and read the text before we do any lecturing. When you do that, that will open up this possibility. If you come to the lecture with questions, I may be able to answer those immediately or in my lecture. And then if I can't answer those through what I have presented, we can have a discussion about, oh, okay, well, what does this problem actually mean? Other places that you can do that is if you have a homework question, most appropriate place to post that is in Canvas. So if you're like, I don't know how to solve for this equilibrium concentration, can you guide me through it? Then what I will do is because I have a tablet here, right? I can just write all of the problems on this screen. I can just copy and paste this into Discord. And then you can see that and then respond to it. And then I can adjust from there. So with regards to homework is optional in this class. I'm going to give you a series of homework problem recommendations that you should definitely attempt. Do as many as you can. If you have done them and you still don't feel confident, do them again. Homework is not produce. It does not go bad. If you do a problem and you're like, oh, I just did this problem. I already know how to do it. Congratulations, that's called learning. So if you don't understand a problem, do it again. Do it again and again and again until you have just basically like, oh, okay, I see why I do this step next. Or I do this step and then this step and this step, and that's how I get the answer. And then, yeah, ask me questions. Probably the most important thing that very few students do, which surprises me because you're literally paying me to teach you this stuff. So ask me questions. This is my job. Get your money's worth, right? All right. The last thing that I want to comment on is about how much time do you need to spend in this class. So on average, when we collected that data for student performance and student time invested, we found that the average C student spent 2 hours per day, so this is 14 hours a week, to get a C grade in Chem 163. So basically what that means is you are going to be taking this course as roughly half of a full-time job. Now, if you are working 40 hours a week or you are taking 16 other credits, you are going to run out of time very, very quickly. Because the only way to get through this course is to put in the time. We're going to be doing a lot of algebra, and algebra isn't super intuitive. It's a practice of, hey, I'm going to do this step, then this step, and you do it enough times and you get the muscle memory, the mental muscle memory. If you don't have enough time to put into it, this is going to be really rough for one of us, and it's not going to be me. So please keep that in mind. This is a 5.5 credit course. I'm going to make you work for it. That is not a threat. That is a warning. And I'm not saying that, like, with a smile on my face, like, I love it when my students suffer. It's just the harsh reality of chemistry. Like, there is so much stuff that we're going to cover, and a lot of it's really fucking cool. But in order to understand it at a level of detail that'll make you proficient, we have to do tons of math. And in order to get there to the point where you can do it at the skill level of, say, me, who's been doing this for 10 years, you're going to have to be doing a lot of problems in a very short amount of time to at least temporarily get that proficiency. If you get an A in this course, you could effectively teach it, right? That's what the A grade means. So if you want an A, you're going to have to do your best to not only do the problems, but also explain to others how they work. So forming study groups is very effective. The class Discord will have voice channels. If you want to meet in the voice channels and ask questions, you can even pull me in there if you want me to, like, facilitate a discussion. I'm happy to do that. But please use all the resources that you have and put in the time. And if you can do that, then you will be successful at this class. All right. Now, normally I'd have you all talk to each other, but you sort of have the chat to do that. So instead, what I'm going to do is just say, go ahead and talk to each other in the chat. I see a bunch of people said good morning. I'm sorry that I didn't get around to saying good morning back to everybody. Give me a second to load the next set of slides. I do want to save that, actually. Oh, and I can erase this because... Let's see here. We are doing chapter 13. So, screen is still blank. It should pop up in just a second. Right there. Oh, my screen is loading. Sorry, hold on. All right. In Chem 161, you talked about electronic structure of atoms. We did quantum mechanics, and we basically started the concept of atoms first. We said, this is what an atom is. This is all the things an atom can do. Here's how it bonds to stuff. In 162, we started you doing calculations with reactions. And we said, okay, if you take a bunch of atoms, you make molecules. If I take molecules with these properties, I can do these sorts of reactions. And we analyzed all of those things quantitatively. 163 is going to try and put both of those things together, with more of an emphasis on the 162. So we're going to introduce a new topic called equilibrium, which is sort of a rude awakening, I guess, in the sense that, hey, we've been lying to you in 161 and 162 to some extent. But it's not much of a lie. It is just a simplification. We're going to introduce this notion that if a reaction can go forward, can it undo itself? Can it control Z? And it turns out that it kind of has to. On the screen here, I have the reaction of hemoglobin binding oxygen to its iron receptor. Now, this is how your body transports oxygen from the lungs to the mitochondria. It uses this porphyrin ring, which is what all those ends are hovering around the iron. So there are actually a bunch of, like, carbons and stuff going around. Oops, let me get the pen out again. Going around this right here, so all of those nitrogens are connected to this, like, wide ring sort of thing that encapsulates itself around iron. And then on the other side is one end of a histidine chain on the hemoglobin protein. That leaves this site right here where the blue dotted line is open. And what ends up happening there is oxygen bunks into it and goes, whoop, it sticks. Now, it doesn't stick super well, because if it stuck super well and only the forward reaction occurred, we would just end up with hemoglobin with oxygen stuck to it. So you take a deep breath, and then the oxygen in your lungs would then be absorbed into your blood, and it would stick to the hemoglobin, and then that's it. That's all that happens. Your hemoglobin has oxygen. I know somebody else needs this oxygen, but that's too bad. It's stuck. I can't get rid of it. And then you die of asphyxiation because your mitochondria can't get oxygen, and that's no good. So, in order for the body to be able to facilitate the transfer of oxygen to where it needs to go, we need to be able to undo this reaction. There needs to be some process or mechanism by which the oxygen falls off and we get the reactants again. Now, if it is way too easy for one of these to happen, we won't get a significant concentration of the other thing. So if it's very easy to form this complex but really hard to give up that oxygen, I never get enough oxygen. Likewise, if I don't have a way to stick the oxygen onto the hemoglobin, like it falls off 95% of the time, I won't get the oxygen where it needs to go. And again, I don't get enough oxygen, right? So depending on the reaction that you're going to look at, the equilibrium is going to be in some spot. Do I have 50-50? Do I have mostly reactants? Do I have mostly products? What is it? Our job in this course, and in chapter 13 and 14 and 15 actually, is to explore equilibrium. Like, what is it? What are all the different possibilities? How does it work? So that's our intent. We're going to look at a state of a reaction called equilibrium. Specifically, I'm going to assign the term dynamic to the word equilibrium. Dynamic means that both reactions, forward and reverse, are occurring at the same time. So it's not like you get to a certain concentration and then hit pause. The reaction doesn't just stop and then the molecules all freeze in place and go, oh, we're at equilibrium, you guys, we can't react anymore. That doesn't happen. Dynamic equilibrium means that both reactions occur simultaneously. Now, the term equilibrium means that the amount of stuff that you have, in other words, its concentration, of both your products and reactants will remain constant. What does it mean for it to be constant? We're going to write this out in algebra. So if I have this reaction, A turns into B, then A at time 0 will equal A at time, or not time 0, sorry. Because at time 0 the reaction starts, but A at time X will be equal to A at time Y. If equilibrium occurs before X. Okay? And the same will be true of B as well. So the amount of B at time X and time Y will be equal. What this is not saying, so this is true about equilibrium. What this is not saying is that the amount of A at any given time will be equal to B. Okay? This is not true. Okay? You can have different amounts of stuff at equilibrium. What's important is that the amounts are constant relative to the amount of time that has passed. The amount of reactant versus product is independent. Okay? So do not equate equilibrium to equal amounts of reactants and products, because that is almost never the case. It means equal over time. All right. I believe I have this crazy British video. Yeah, here it is. So I have this really creepy British video about equilibrium that I post. Yeah, I know my browser is up to date. Don't do this. I hate when YouTube does this. Let me just click on it again. There we go. Oops, you can hear the music playing, unfortunately, but I have to actually capture it. All right. So this is going to show a visual example of equilibrium. And it's going to talk about open and closed systems, which is going to be particularly important. However, there's also this really creepy echo in the background, and I kind of love/hate it. Enjoy. Here we go. We'll just watch this for a bit.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation.
So I'm going to hit pause real quick. If you hang laundry out to dry, eventually it gets completely dry. This is an example of a reaction that would not occur in the reverse reaction. Your towel does not spontaneously collect water vapor and become wet. That's not how drying works, right? So it is typically very dry outside when you would hang up your towel to dry. So this reaction is not at equilibrium. This is the sort of process that we would have talked about in 161 and 162, where all of the reactants, all the liquid water, you can't see my cursor, there we go, all the liquid water would turn into water vapor and then go away, and it would not do the reverse. So we're going to talk about equilibrium systems where the reverse is possible. So let's look at that.
This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow.
Oh, I'm muted again. There we go. Sorry, I'm muting myself during the video. Okay, so in this case, what's going on here is that I have water molecules that evaporate, and so they're in the headspace right here, right? Up in the top. And they'll bounce around inside this closed system duffel bag. But at some point of them bouncing all over the place, they may bounce in a direction that orients them towards the towel again. And because they're restrained here in this space, eventually this will happen. Water molecules will evaporate, bounce around, and then go back towards the towel, where they'll condense again. The reason that the molecules are guaranteed to go back is because the system is closed. In an open system, the molecules would just escape, kind of like if it was the towel out on the line. But here, the molecules are stuck. Eventually, they will return to the towel. And so the towel will never dry. It will remain damp. At some point, the amount of molecules coming off of the towel will equal the number of molecules rejoining the towel, and that is the point where you will hit equilibrium, because if for every molecule that pops off, a molecule will rejoin, then the amount of molecules in the space up at the top will be constant. They won't be the same molecules, but the number of them will be constant.
Dynamic equilibrium only occurs in closed systems.
All right, there's our creepy equilibrium video from the Brits with their crazy torches and their echoey nonsense. All right, so that's our visual video example of equilibrium. Here's what this would look like graphically with some data. On the screen here, you can see that after a certain point, the amount of stuff that we... Oops, I'm sorry. The amount of stuff that we have remains constant. So as I react N2O4, I use it up. So the amount that I have goes down. As I react N2O4, I create NO2, so the amount of NO2 that I have would increase. But if two NO2s bonk into each other, they can react to form N2O4. As I make more of these, it's more likely that those are going to encounter each other and turn back into the initial reactants. And thus, the speed at which I am making these will decrease. So, if the reverse reaction was not possible, here's what my speed would be. It would just continue up in a straight line, right? And this would be NO2. And what would happen to N2O4? Well, it would do something like this, right? Until it hit 0. So if this was irreversible, this is what would happen. You would just lose things at a constant speed, right? But because the reaction is reversible, it starts to decelerate. And eventually, the rate at which we are gaining or losing products, depending on which, or substances, depending on which side of the arrow you're on, becomes steady. And that's when you're at equilibrium. Now, down here, I have kinetics. We're going to talk about all of this in Chapter 17. So don't worry about what's meant by rate. Rate is just the slope of the top diagram. So if I take the derivative of this, or deconcentration dt, I will get the rate. Now, if you've taken Calculus 1, you know what that means, taking the derivative of something. If you have not taken Calculus 1, don't worry about it. We're gonna talk about that later. That's Chapter 17. Here's another visual example of this. I don't know why this is appearing so slow. Do I have text on there? I don't. Okay. So, in diagram 1 right here, or A, I guess, you'll notice that I have only reactants. So I only have these two. There are no products to be seen. So we're at this state right here. No products, only reactants. Then as time goes on, I start to generate more and more products. Sorry. I'm just underlining all of the products here. And so if I were to count these, I have 5 products, and then I have 8, and then 8. Once I hit equilibrium, I'm going to have the same amount of products over time. I will also have the same amount of reactants. So if I went and counted reactants, I should be able to see there that, like, oh, okay, there's only 4 of each. And it will remain like that forever. All right. What types of things are at equilibrium? Turns out virtually everything. Virtually everything around you is at equilibrium. So, for instance, wildlife populations. If you have some sort of predator, like, say, a wolf. Let's see here. So here's my wolf. And I don't know why he has whiskers, actually, now that I think about that. And we'll give him teeth or something. And then you have, like, prey, like a bunny. I'm basically drawing a peep, I guess. Okay. There is an equilibrium between these two. If predators hunt all of the prey from the ecosystem, then the predators will eventually starve, right? And so the predators will eat some of the prey, but not all of them. Because if they eat all of the prey, then there is no more prey left, and then all the predators die, and then everything is dead. Likewise, if there are no predators, then the prey would multiply out of control, and then they would consume all of their resources and starve themselves too. So, by virtue of just existing, the predator-prey dynamic is at an equilibrium. There is roughly the same amount of wild rabbits and wild wolves in this fictional ecosystem that I have made at a given time. In biological systems like the ocean or the atmosphere, you also hit things like equilibrium. So the ocean will have regions of different temperature, and they will equilibrate based on current and stuff like that. And so all of the things in the environment react to stimuli to try and get to equilibrium. For example, wind. Wind is a function of pressure. If you pressurize one location by like heating it up, for example, then wind will move in the direction of high pressure to low pressure to equilibrate all of the pressure. And that's so you get a dynamic system, which leads to weather. Typically speaking, if things hit equilibrium, then that can be bad. For example, if your body reaches dynamic equilibrium, you die. Obviously, that's not great, right? Like, we do not want to reach equilibrium where the reactions that are important for sustaining life go in reverse and then you die. That's not fantastic for anybody. But equilibrium implies that the intent of the reaction is that it is moving towards this state where the forward and the reverse reactions can occur at the same speed. And like we've said before, the amount of products and reactants will not necessarily be the same. That has to do with thermodynamics, and we're going to talk about that probably a little bit in chapter 14, maybe at the end of this chapter. All right. This is a 2-hour class, and so what that means is that every hour, we're at 10:56 right now, so we're going to take our break. Let me find my cursor there. There we go. So I put this screen up, and then I put a timer up, and then I play music from whatever it is that I've been playing for my, whatever I've set. So this week, oops, I didn't move this over because it was much shorter than the last name that I had. I've been playing Tunic. If you like Zelda games, it is a Zelda Dark Souls-like game, which I initially didn't want to play, but then somebody sold me on it because it has something under the hood going on that I found very, very interesting, and it is fantastic. I've almost finished it. So you're going to be listening to music from that soundtrack during the break, should you choose. So please enjoy that. If I could find the window I had it in, there it is. And then let me unmute this. All right, there we go. All right, we'll see you in a bit. Alright, we're back. Wow, it's not often that I get that right on the first try. Oops. I'm gonna turn this down here. And then let me mute it on my end so I'm not listening to it. Alright, so we have defined equilibrium. Excuse me. Yes. There's someone who wants to say hi to you all. Hold on. Oh, come here. Come here, Maya. Hi, Maya. Say hi. Hold on. This is Maya. Say hi. Maya. Maya. Maya is my cat. If I knew how to configure a webcam button here, I could just show her to you. I could do that later, I guess. But if you hear just random meows or purring in the background, it's because Maya has like a little perch that she can sit on right next to my head. Um, and she likes to do that. She's now going to go to the window where she can admire all of the peasants outside, the peasants being me and everybody else that walk by. So yeah, we may get interrupted by Maya on occasion. She is beautiful and queenly and a nuisance. All right. So we've talked about what equilibrium is, the general concept of it. Now what we're going to do is we're going to try and represent with a number, because as human beings, we like to quantify things by applying labels and numbers to them to give us a better understanding. And for equilibrium, it just comes down to a matter of defining it. So here's what we're going to do. We're going to define the current state of a system by using this. It's called the law of mass action. The law of mass action is a model. It is strictly something that we have made up. So what it says is that if you do this operation, you will get a number, and that number is K. Now, what operation did we do? So here we have reactants, and here we have products. And what we have done is we have taken any coefficients, and we have made them powers. So coefficients become exponents. And then we just say, okay, products over reactants. And specifically, we care about concentration. So if I have some reaction, I could punch in all of these numbers, and I would get a value for K. Now, specifically, the numbers that we'd punch in, these concentrations would be the concentrations at equilibrium. So once a system is at equilibrium, you could measure the concentrations and then calculate K. In fact, next week you're going to do that. I'm going to give you a bunch of solutions. I'm going to say mix these together in these specific ratios, and then you're going to throw them in a colorimeter to determine their concentration. And from that, you will be able to figure out what the equilibrium constant is. Because you'll know how much you put in there, you'll know how much you started with, you can do subtraction to say, oh, I must have turned this into that, and you'll get an equilibrium constant. So, oh my goodness. Hold on. Someone is power washing outside, and my window is currently open. And I need to close it. Which is fine. Sorry, hold on. There we go. The guy couldn't hear me. Poor Maya. Sorry, that was just incredibly amusing to me. Maya's sitting at the window looking outside the screen. And I heard the guy power washing, and I was like, oh, I thought they were supposed to be done with that. She just got sprayed with water. My couch is all wet too, but I don't really care about that as much. I can clean that in a bit. Ooh, I do care about the chlorine smell. That's not great. Oh well. Alright, sorry for that distraction there. I was not expecting a blast of water to come in the window. Okay. Alright. Now, A and B as concentrations, also C, D, whatever things are in our thing, are going to have units of molarity. So the units of this are moles per liter. Now, K is a dimensionless entity, so no units. And you might think, well, that's kind of weird. What if I have different values of C and D on the top versus A and B, and like the molarities don't cancel out? How do I get no units? We're going to talk about that in just a little bit. All right. How big or small is K? Like, what does this mean? Well, let's look at this mathematically before I put this on the screen here. So, if K is just whatever the product's concentrations are over whatever the reactant concentrations are, and then like some powers and stuff like that, let's suppose that I had Let's suppose I had tons of products, but very few reactants. What would a big number divided by a small number be? I'll give you a second to think about that. If I had a large number divided by a small number, what type of number would you expect? You could type this in the chat. Big number, small number, 1. Like, what do you think you would get? I just need a second to drink some water there. But hopefully, if you had a big number divided by a small number, you would get a large number. Yeah, there you go. People are starting to... It takes a second for the answers to come in, I realize, so... But yeah, a big number divided by a smaller number would be a large number. So if you get a k that is a large number, that must indicate that you have lots of products. Now, what if I do this? So we're going to write the expression again. And so I'm going to say I have few products, but lots of reactants. So what would K be in this case? So if I have a small number divided by a big number, I would get a small number. Now, what would these numbers be relative to, say, if they were the same number? So if I had products and reactants were equal, I would get this, right? Because the number divided by itself would be 1. And so this is our range of values for K. If you have lots of products, you get a big number. Big number meaning K is greater than 1. If you have lots of reactants, you'll get a small number. K is less than 1. And that is simply a result of the math that we have created. Now, I'm doing a very simplified version of this. I don't have any exponents. All I have is one reactant, one product. But it will work regardless of what exponents or what powers or how many of what you have on each species. So, this is the gist of it. K is greater than 1, mostly products. K is less than 1, mostly reactants. K is equal to 1, you have 50-50 of both. And so that's what this is showing. So the thing that you will want to remember is that equation I showed you on the previous page, the law of mass action. And then from there, you could just derive everything as in terms of products versus reactants. All right. So let's suppose that I did a reaction and I got K has a value of 100. What does that tell you? More reactants or products at equilibrium? You can type your answer in the chat. And what I'm going to do is I'm going to say that this equals 100. So there must be more products, and let's mathematically show that that's the case. So in order to get 100, I would have to have something like this. Right? And then these would cancel, and I'd get 100. So I'd have to have 100 times more products than reactants to get a K of 100. So that's how simple calculations with the equilibrium constant can be determined. Now let's suppose that I tell you what one of the reactants is. So if I know that K is equal to products of reactants, let's actually fill in what these are. So here are my products, here are my reactants, and I know that A is 0.6. So what I could do is I could rearrange this, the expression, to solve for B, right? I just multiply both sides by the concentration of A. And so that would be 100 times 0.06, which I believe is just 6, right? So you can see where the rabbit hole on this is going to lead, right? I'm going to give you a K value, and you're going to have to tell me A or B. Or the other way around, I'm going to give you A or B, and you have to give me K. One of those, it turns out, is much easier than the other. We're going to do the easy ones first, probably today. And then on Wednesday's lecture, we're going to do the more complicated ones. All right. Now, because the law of mass action is a quantity that we can calculate from the stoichiometry of a reaction, we can manipulate it using similar techniques to, say, Hess's law. So you might remember with thermodynamics, where if I had a reaction like this, and I knew what its enthalpy was, we'll just say, like, I don't know, minus 250. And then I did this to it. If I can get the right color. If I multiply this by 2 and put 2's in front of all these things, I also had to do that over here, right? So hopefully you remember doing that in 162, where you take an equilibrium, or not equilibrium, sorry, a reaction expression, and you would multiply by a number, or you could add things together, and then you'd sum their enthalpies. We can do similar stuff to that in this, but because the law of mass action involves exponents, we had to do slightly different we have to do slightly different math. So instead of negating something, we're actually going to invert it. So in Hess's law, if you reverse the reaction, you would flip the sign on your enthalpy. Well, K can't be a negative number. You can't divide two positive numbers to get a negative number. Instead, what we do is we take its inverse. We raise it to the power of -1. So, for instance, let's suppose I have this reaction. A plus B produces AB, and here's my equilibrium constant, K. What I'm going to do to this is, if I reverse the reaction, the K reverse is going to be its inverse. Now, why does this happen? Why is it not like a negative sign instead of an inverse? Well, let's do some algebra. All right. So here is K for the initial... Oh, I need to make this bigger than 1 pixel. Sorry. That's too big. There we go. That's better. Okay. So let's write that reaction down. And then I can write its equilibrium expression. Now, what would the inverse of this be? What is an inverse? An inverse is dividing something 1 over that thing, right? So the inverse of K, which I'm going to call K prime, would be 1 divided by K, or the reciprocal, right? So I should just take the reciprocal of this thing right here. And so that would be this, right? And if the top is products and the bottom is reactants, then that means that the reaction that this is representing is this reaction, right? So by taking the inverse, I got the reverse reaction. So I will get a different equilibrium constant. So that's why we can't just flip the sign, because when we do the algebra for this, it doesn't work when you do that. So if I try and figure out the reverse reactions K, all I do is take the inverse. You have a button on your calculator. Where is my calculator? Let's find the calculator. Oh, it didn't appear. Hold on. What is this? Oh, that is there. Oh, it's because it was minimized. Okay. Let's put the calculator on the screen here. Oh, sorry. Hold on. I'm trying to resize the chat here. So we'll put the calculator on the screen, and we'll just type in numbers. So if I have a button like this, so 15000. So this is 1.50 times 10 to the 4. If I hit this button right here, 1 to the x, I get the inverse. Boop. There you go. So this is just taking the number that I printed and dividing 1 by that number. And if I do it again, boop, I get the number back. Because all I'm doing is flipping this up and down, right? So same with K. All right. Now, if you multiply a reaction by some constant, so like 2, 3, 6, whatever, then what you have to do is you need to raise the equilibrium constant to that power. And so an example like this, where I have C plus 2Ds combined to make CD2, here's my equilibrium constant for that. If I were to multiply the entire thing by 3, then what I would do is raise it to the power of 3 for my equilibrium constant. Oops. Sorry, that's a bad line. I'm using my mouse for this one. Oops. We can show that algebraically too. So again, we'll just do this. How do I want to rate this? Let's write it out, the whole thing, actually. Oops, hold on. I was using this during spring break to, like, actually do image editing. So all my settings are not set to lecture staff. There we go. Okay, so our reaction was... Why is nothing right? Oh, because I'm writing with the eraser. Crap, hold on. There we go. So there was our equilibrium expression. So I would rate this. So products over reactants. Now the 2 appears because I have a 2 as my exponent, right? So we'll make sure to include that. And then what I want to do is I want to multiply everything by 3. So that would be, this is a 3, this becomes a 6, and this becomes a 3. So what ends up happening? Well, this becomes a 3, this becomes a 3, and this becomes a 6, right? Or in other words, if I were to undo each of those, I do that, which is the same as me just taking whatever number I get and cubing it. So if you multiply a line through with a constant, you raise your equilibrium constant to that power. And then finally, if you have a new reaction that you have created by combining previous reactions, in Hess's law, you would have just added everything together. Here, you're going to multiply. And so I'm going to show you these two reactions and then the combined reaction. So this line that I'm going to draw in here is our result, because I can cancel out these two when I combine these reactions together. The new K for this will be the product. And let's show that that is algebraically sound too. I like showing you guys the algebra because it helps some people. If you hate algebra, that's okay. All right, so let's show that if I have this is reaction 1. Ifs, hold on. I can't read the reactions on my screen here. So A becomes 2B. And then 2B, which is reaction 2, becomes 3C. And so I have K reaction 1 and K reaction 2. So the overall reaction would be A eventually becomes 3C. And this would be K3. So if I take K3, that should be anything that equals this, right? C cubed over A. Now, if I were to write K1, that would be this. B squared over A. And if I were to write K2, that would be C cubed over B squared. Now, what I'm going to do is I'm going to do some math trickery, okay? So watch carefully. I'm going to take this and put it here. And then I'm going to take this and do nothing because I have the wrong layer selected. There we go. That should work. And you'll notice that if I arrange these two things like this, where I say, oh, okay, I'm going to multiply them together, what happens? Well, this cancels out with this. And lo and behold, what's left over is exactly what I expected it to be. So when you sum reactions together, doing the Hess's law sort of thing, remember that you can't just add the equilibrium constants together. You have to multiply them. That's just how the math shakes out when we do it. All right. So those are a selection of things that you can do to equilibrium constants once you have calculated what the equilibrium constants are. So we're starting by just doing a bunch of things to different reactions with numbers that have already been solved for. So here's your first demonstration problem. What I want you to do is I want you to tell me if the equilibrium constant to the top reaction is 109, I want you to tell me the equilibrium constant for the bottom reaction. So I've done all of these things together. So you're going to have to, excuse me, seltzer water. You're going to have to do all of the things that you did in sequence. So you have to multiply by some number, and then you might have to invert it, and then you might have to multiply by all sorts of things. All the three examples that we talked about, put them into practice right here. Tell me what the new equilibrium constant is. I'll leave you 2 or 3 minutes to go over that on your own. Type your answer in the chat when you got it, and I'll go over the answer with you once I am back. So see you in a bit. All right, let's go over the answer here. I need both pieces of information on the screen here. So we'll just do that. All right, so we know that this top reaction is that. And so what I need to do is now I need to make this look like the bottom reaction. So the first step that I was going to do is I'm going to reverse the reaction. And so if I do that, my new reaction becomes this. So G2E plus 3F. What happens to K? So K becomes reversed, which equals 109 inverted, or 1 divided by 109. And then for step 2, to make it match, I need to multiply by, I think it's 3. So multiply by 3. So that would give me 3G. And that's going to make 6E and 9F. And I believe that I just have them, I have F written first for some reason, just to keep you on your toes. So since I multiplied by 3, I need to raise K, we'll call it K new actually, equals. So I've done this, now I need to cube it. Well, if I have two exponents, I just multiply them together. So my new K will be this, 109 raised to the power of negative 3, which we can just type in our calculator here, which is still on the screen conveniently now. 109 raised to the power of negative 3. Boop. There you go. 7.72 times 10 to the minus 7. Very good. Now make sure that you are doing all your algebra before you punch it in the calculator, because the more keystrokes that you have to type in, the more likely it is you'll hit the wrong keystroke. All right. So that was how you do this by applying multiple of the permutations at once. So I'm going to put some more of these up on the screen for you to try. Oops. There we go. So I'll have you try this one. I'll give you 2 minutes to do it, 2 or 3 minutes. So I have the reaction shown at the top with a K value of 2.2 million. I want you to give me the equilibrium constant for the reaction shown below, which has a bunch of fractional numbers in here. Now, you can't have half a carbon, obviously, but mathematically speaking, these formulas are constructs, right? This is all models. So if you could theoretically have this reaction, you could calculate a K for it. And theoretically, that could be useful for various applications. So go ahead and do the equilibrium constant for this second reaction right here with the star that I just wrote. And we'll go over the answer in about 3 minutes. So I'll see you in a bit. All right, 1 more minute and we'll go over the answer to this problem. All right, let's see if we can do this. I clicked the wrong thing. There we go. All right, let me clear all this out of the way. I gotta find my pen. All right, so I have this reaction here. I gotta make this window bigger so I can actually read these reactions. My preview is just way too tiny. There we go. All right, so I'm gonna reverse the reaction. So that would be CO2 plus CF4. Turns into I don't know what COF2 is. It's like some sort of formaldehyde with fluorine derivative. So this would be, so K after step 1 would be the inverse of 2.2 times 10 to the 6. Because I reverse the reaction. And then the step 2 would be to multiply by, what are we multiplying by? Looks like by a half, so multiply by 1/2. Now I'm treating this like a multiplication because what do we do with division, right? We said for multiplication, you raise to an exponent. What would the opposite of that be? Well, you'll see in just a second. So if I multiply by 1/2, I would now get 1/2 CO2 plus 1/2 CF4 makes 1/2 of 2, or 1 COF2. So K for step 2 would be, so there's what we had. Now we're going to raise it to the power of 1/2. Well, what happens when you do something to the power of a fraction? That's the same as doing that, right? Square root. So this would be that. And then because it is in a fraction, or because it's in the square root and raised to the negative power, it's just the inverse of this. So 1 divided by the square root of this number. Oops, sorry, I didn't mean to click that. So there you go. That's what our K value equals. So we'll punch that into the calculator. Alternatively, I could just combine these exponents right here. So -1 times 1/2 is -1/2. So that's what I'm going to do when I type this in the calculator here. So there's my 2.2 times 10 to the 6. I'm going to raise it to the power of parentheses -1 divided by 2. And I'll hit enter. And that's what I get. I have too many sig figs, sorry. All right, there you go. Now that should make sense because if I had a big K, oops, sorry, up here is my big K. If I had a large K for this reaction, reversing the reaction should mean I have a very small K. Because here I have mostly this stuff. In the reverse reaction, I would still have mostly this stuff. But the value of K is adjusted accordingly. All right. One more problem for you to try before we go. I want you to give me the equilibrium constant for that reaction. And let me just see if there's anything after this. There's not. Okay. So I'll give you 2 minutes to try this. We'll go over the answer, and then we're all done for the day. So see you in a bit. All right, one more minute. We'll go over the answer. All right. So we put that on the screen there. And so let's combine these two reactions here. So first I got to write down the reactions so that I can manipulate them. CO and H2O makes CO2 plus H2. All right, and then I've got CO plus 2H2 makes methanol. And, oh, that's it. Just methanol. And the equilibrium constant for that is 1.4 times 10 to the 7. And so what I want to do is I want to manipulate them to make, so here's my target equation. All right, so very clearly, this is on the wrong side, and this is on the wrong side. So I need to reverse this equation. So I'm going to do that down here. So CO2 and H2 makes CO and H2O. So this will be 1 times 10 to the minus... Oops. There we go. Oh, I put the minus in there. That's not what I meant to do. Sorry. So 1 times 10 to the 5, positive 5, raised to the negative 1 power. And then the other expression, I just kind of copy this one, right? Well, if I do that, it doesn't capture everything. So I'm just going to copy, paste. We'll just put this down here. And then when I sum these together, this cancels out with this. And I get CO2 plus 3H2, because these will sum together, makes methanol and water. And that's our target equation. So what do we have here? Well, we have this K1 reverse times K2. So K1 reverse times K2 must equal the new K. And that would be that. So we'll type that in our calculator. So 1.0 times 10 to the 5. We're going to invert it. So we got that. We're going to times it by 1.4 times 10 to the 7. And so we get 140. Oops, I don't need that dot there. I only need 2 sig figs. There you go. All right, so now you know how to manipulate K with various equations. We're probably not going to do this terribly much until you least expect it. And then you'll be like, oh shit, yeah, that thing we did on the first day of class. Yeah, what was that? Because this is one of these tools that like you want to keep in your toolkit And it's going to come in handy when you least expect it, because you're trying to figure out like the equilibrium of like this reaction, but you have no idea how to do this in the lab. But you could do two other reactions that are much simpler and get their equilibrium constants, and you just multiply them together to get a new to get the new expression, because you could just sum the reactions, right? So in the laboratory, not every reaction is practical. We're going to run into this in the experiment too, where trying to figure out what the equilibrium constant for a specific reaction is impossible, because both a product and a reactant both can be titrated with thiosulfate and react, and so you get no answer if you do that. But if you aim for a different set of reactions and then multiply those reactions together, their equilibrium constants, because you can add the reactions together to get the product, then you get the answer. And so that's what we're going to do. So keep these tools that we covered in your mind, because they will come in handy in very, very specific circumstances. But that's all I got for today. So we went over by 3 minutes. I apologize. I'll try not to go over in the future. I do want to thank everybody for coming out to the lecture. This is the first of 40, I guess. So we will be back here on Wednesday to go over more Chapter 13. We'll probably get through probably the first half, if not a little more than that. And then hopefully we will finish that up next week so that I can, assign the quiz and you can turn it in on Friday when we actually meet for lab. So again, thanks for coming out to the lecture. I hope that you found it useful and also possibly entertaining. Tune in on Wednesday when we come back for more. If you have any questions, let me know by email. Happy to answer them. We'll get the class Discord set up. I'll see you on Wednesday. Take care.